Hi, everybody. Bonjour. We just want to let you know that the broadcast for this that's happening on YouTube starts live right at 2 p.m. It doesn't tell me when it starts, it just starts. So if we can be ready to roll right when 2 p.m. hits, the time is there. That's great. I'll tell you right now, please, just before that, if you could please make sure your cell phones are off, silent, at least off is best. We are recording this and we have some photos being taken, so there will be some evidence for all of you to access after the fact, and we'll start right at 2 p.m. Thanks. All right, welcome everybody. Come on in, please. My name is Sydney. I am the chair of the Water Engineering Technology Department, and over the past 2 years, I've had the pleasure of teaching all of the students you will see today, all of their chemistry courses. Something is happening. Okay, so thank you all for being here. We are streaming this live, and it's my pleasure to welcome you all today to the year-end capstone presentation for the Water Engineering Technology program. This event marks a significant milestone for our students, and we're really excited to showcase the hard work, dedication, and passion that they've all put into their capstone projects over this past semester. The Water Engineering Technology Department is designed to equip our students, and ultimately our graduates, with the skills that they need, in both in terms of technical skills, critical ability to think, and practical knowledge that they are going to need out there in the workforce to address the many challenges faced by the water industry today. Today, our students will present to you a variety of topics that tackle real-world problems in the water sector. These projects reflect not only the expertise that they've gained during their studies, but also their commitment to finding practical and sustainable solutions to improve water systems and manage water resources more effectively. We are incredibly proud of each and every one of the students you will see today for the determination and creativity that they have shown. So this afternoon, we will have 3 groups presenting for you. The presentation should be about 15 minutes, after which we'll provide a 5-minute period for questions from the audience. So if you get a question while they are presenting, please hold that question in your mind, and we encourage you to engage with our students during that question period. After the first 2 groups, we will have a short break. There is a coffee station just outside, so if you need to get out there and grab some caffeine, a washroom just down the hall as well, we'll provide some time to do so. This time, please turn off your cell phones. Have those on silent, please. And I would like to invite the first group, the waterbenders, up to the stage. And while they are coming up, I'm just going to give you guys a little bit of an introduction to the presentation you'll see today. Make sure it's on. So our first group this afternoon is going to present their study, which focused on investigating the potential causes of some ongoing water quality issues in West Kelowna in the Rose Valley distribution system. The research explores the potential causes of excessive manganese concentrations by examining some key water quality parameters, such as iron, phosphorus, nitrogen, dissolved oxygen, oxidation reduction potential, you name it. The main focus of this first group was looking at the watershed, so the two water sources for the Rose Valley Reservoir system, Esperon Lake and Bighorn Reservoir. The group will then finally propose some potential solutions to improve water quality and sustainability for that water system. So please welcome to the stage our first group, the Waterbenders.
All right. Well, good afternoon, everyone. My name is Riley. These are my colleagues, Enzo, Garrett, and Rosie. Today we're going to be talking about managing manganese. And we picked this topic because we feel like it hits close to home. So I'm going to hand it off to Rosie now, and she's going to give you a bit more detail about that.
This is the Rose Valley Reservoir in West Kelowna. They've recently been having some discoloration issues in their distribution system, and that's what sparked this project. We wanted to look at the upper reservoirs that feed into the lake and collect data that could help determine what exactly is going on. For years, residents of West Kelowna receiving water from the Rose Valley Reservoir were exposed to frequent boil water notices. This sourced from turbidity issues, so that would be large amounts of suspended particles in the water that made chlorination less effective and, according to interior health guidelines, required boil water notices. The construction of the new Rose Valley water treatment plant started in 2020, and it began operation at the beginning of this year. Customers started to experience discolored water with a metallic odor coming out of their taps. Up there you can see pictures that people took of the water that was coming out of their taps. So it was determined that the source of this discoloration was manganese in the water. And this is a different issue than what was happening previous to the construction of the treatment plant. Normally, in a lake or reservoir, the conditions are such that manganese becomes a solid and sinks to the bottom of the lake. However, in the Rose Valley Reservoir, these typical conditions were not occurring, and manganese was dissolving into the water that was entering the treatment plant. When this happens, the water looks clear, but when chlorine, which is an oxidizing agent, is added, the manganese turns into its solid form, which is colored, and that's what people were seeing coming out of their taps. I've got a demo to help visualize this. I'm starting with water that has a large amount of dissolved manganese in it in the graduated cylinder that you see on the right, and you can see that it is clear. Here I am adding a bunch of chlorine into the graduated cylinder, and you can see the manganese precipitating out and becoming that brown color that you saw on that earlier slide. For the sake of the demo, I added a really strong chlorine concentration so that this reaction happened immediately, but up at the treatment plant, they're dosing much less, and this reaction takes place over time. So the water leaving the treatment plant will still be looking clear, and this color and odor change will be happening over time as the water moves through the distribution system towards people's taps.
So the scope of our project included looking into the water quality parameters of Rose Valley watershed. Specifically, we were analyzing the concentration of manganese, iron, phosphorus in Bighorn Reservoir and Esperon Lake, which feed into the Rose Valley Reservoir. We also observed oxidation reduction potential values and how water body is either in an oxidation or reducing state, which determines if certain elements stay in solution or precipitate out. We've also come up with some possible recommendations that could help resolve these issues.
We went sampling on October 18th, and we went all the way up to Esperon Lake and Bighorn Reservoir. These dammed lakes are the water source for Rose Valley Reservoir and can be opened and closed depending on the needs of the reservoir. At the time we were sampling, they were not open, so there was no flow between reservoirs or down to the Rose Valley Reservoir. Here we have close-ups of Esperon Lake and Bighorn Reservoir with our sampling locations marked. We sampled at one site on each lake. We did sample pretty close to shore, and that is because we ran into some weather conditions and had to deviate from our original plan a little bit.
So the first site we sampled was Esperon Lake, shown on the left here, followed by Bighorn Reservoir on the right. When we arrived at our sample location, we realized the conditions were definitely not going to be ideal for a day of sampling, and we weren't going to be able to go through with our original sampling plan, as you can probably tell in this picture from the snow and the canoe. Despite the conditions, we realized this was likely going to be our only opportunity to collect the samples that we needed, so we decided to go with our alternative sampling plan. This plan meant that instead of collecting a composite sample from various points in each reservoir, we would sample from a single point and have a field split sample. This means taking one large sample and dividing it into 3 triplicate samples to ensure accuracy and precision of lab analysis. So in each lake, we sampled a variety of water quality parameters. First, we took water samples using a Van Doren sampler for lab analysis of manganese, iron, and phosphorus. Secondly, we use a YSI multimeter probe to take on-site readings of dissolved oxygen, pH, temperature, and oxidation reduction potential, also known as ORP.
So right now we're going to give you a quick video on how a Van Doren sampler actually works. So if you look here, you can see this rope, and it's heading up. So that'll be attached to the canoe, and on that rope there's a weight. So when you drop that weight, it hits a contraption at the bottom, locks those 2 suction cups, and you've just isolated a sample at any depth that you choose. Now we're going to move on to lab processes, and I'll give it away to Garrett.
So first I'm going to talk about the atomic absorption spectrometer. Iron and manganese was dissolved into solution through an acid digestion with concentrated nitric and hydrochloric acid. The acid digestion was necessary to get solid iron and manganese into solution because the total iron and manganese is where we were interested in those values. The sample was then taken or concentrated by evaporation, put through a nylon filter, and ran through an atomic absorption spectrometer, which is the instrument shown here. This instrument works is, the way this instrument works is the elements in solution are put into an excited state from their natural ground state by the flame, which is shown right here. An element-specific lamp reads out an absorbance value. The computer interprets these absorbance values and presents a concentration by using the calibration curve created with our series of known calibration standards. The graph is shown right here.
Now for phosphorus analysis, we used a standard hack method. This involved a digestion and analysis with a spectrophotometer. And now we'll get into the results. All right, so the first thing we're going to talk about is phosphorus. So if you look behind me, you can see both Esperon and Bighorn Lake showing an average at about 0.5 milligrams per liter, 0.05. Now you might be thinking that's quite a small concentration, when in fact, if we jump to the next slide, you'll see that this classifies these lakes as eutrophic, which means they have high levels of nutrients and high vegetation growth. When we look at historical data, however, we'll notice that the average is about 0.0125, so it's a little bit smaller, and that would classify these lakes as mesotrophic. So you still get moderate levels of nutrients, and you're still getting vegetation growth. And what happens in these lakes when you have an influx of phosphorus is you get a phenomenon called eutrophication. So eutrophication is going to lead to algae blooms. When you have algae blooms in high numbers, you're going to see, as they decompose and die, you're going to see bacteria digest them. Now these bacteria consume high levels of oxygen, and that's going to lead to low concentrations of dissolved oxygen in the water. Now why does that matter? It leads to ORP on the next slide. But on here, so we're talking about undersaturation of oxygen in Bighorn. which is backing up the first statement about eutrophication. So that's saying eutrophication has happened. On the second one, Esperon, it's exhibiting that happening right now. So why does dissolved oxygen matter? We'll go over to ORP. So what is ORP? AKA redox potential. It's the measure of a lake's ability to gain or lose electrons. So if you have reducing conditions, you're going to have substances existing in dissolved form. If you have oxidizing conditions, you're going to have substances in solid form. So why does that matter? Well, I'm going to hand it off to Rosie, and she'll explain why iron and manganese, what iron and manganese are existing in these forms.
Iron and manganese usually exhibit similar behavior within a water body, so that's why we were analyzing for both. These are some graphs we can use to determine the form that iron and manganese are in within the lake when we sampled. On the x-axis, we have pH, which is something we measured in the field. And on the y-axis, we have EH, which is redox potential, and that was calculated using our ORP measurements that we took in the field. When we put our data on the graph, it shows us that the iron is in a solid form of iron 3 hydroxide in Bighorn, and in Esperon, it's right on the cusp of that and the dissolved ferrous ion. In both lakes, the manganese is in the dissolved manganese ion form, but is close to transitioning over to the solid form of manganese carbonate.
So when we look at the results of these, you see iron in a high concentration there. But as Rosie just stated, it's existing in a solid form. So we're not concerned with it traveling downstream into the reservoir. Manganese, on the other hand, exists in a dissolved form in these lakes. But if you look at the concentrations here, you can see a very, very small number. So we're not worried about that either. Phosphorus, however, is present in significant concentrations, and that eutrophication process I just described to you earlier may happen downstream with these increased concentrations heading into that lake. So that leaves us to wonder, where is the phosphorus coming from? And we believe that it's coming from fire retardant. So the main source of fire retardant used in BC is Phos-Chek. And judging off the name, I bet you can kind of guess what's in it. Phosphorus. But unfortunately, we can't say that as certain. We do not have enough data to correlate those times. We can see historical trends. We can see historical trends and kind of match it up with spikes in phosphorus when the fires happen. But it would require further study to be certain. So now we've got some recommendations. 2 of them are going to deal with algae, and the third is going to be a monitoring strategy. So I'll hand that off to Enzo.
Okay, so our first recommendation to help improve the overall water quality in the reservoirs is the implementation of nanobubble technology from companies like Moliere. Nanobubble technology is an alternative to conventional aeration, where instead of pumping air directly into a body of water, highly oxygenated water is pumped in instead. This results in the oxygen diffusing out and more efficiently saturating the water. This greatly increases the dissolved oxygen content of the water, which can reduce the effects of algae blooms and eutrophication, and raise the ORP values, preventing internal loading of manganese and iron from sediments.
Another recommendation for algae control was an ultrasonic instrument shown up here on the left. This instrument emits ultrasonic waves that interfere with the cell's buoyancy. This affects their movement to the surface to perform photosynthesis and their ability to descend to the bottom of the water column to consume nutrients. Without this ability, they will naturally decompose. Also, as you can see on this instrument, is powered by solar panels, so there's no external power required. On the right up here, it shows the algae upon 10 and 15 days after implementation of the ultrasonic device. From here to here to here.
So our third and final strategy is online ORP monitoring. So as we've established previously, ORP depicts what state an element is going to exist in. So by being able to monitor this at all times, water treatment plants can predict how much or how high of a concentration manganese or iron will be coming through based on the ORP. If it's a high value, we're not going to see that. It's going to settle out and precipitate as a solid. If it's low, you're going to see higher concentrations. So online monitoring is going to be able to provide like a trend analysis, and you'll be able to forecast when these high levels are going to come through. Aside from that, maybe proactively manage it based on those trends. So to conclude this project, I know it was fun. We had a lot of ups and downs, arguments. We all started to hate each other at the end. But we learned a lot, and our teachers helped us out quite a bit. And if we could change one thing, when we went out and sampled, we probably would have looked at the forecast before we went. So as you can see, Rosie and Enzo are out there in the canoe, and that's not rain. It's actually snow. You can tell it's snowing pretty heavily right now. It is rather cold. We're in the negatives, but Enzo is loving it. So is Rosie. They're as happy as can be. And of course, we did think about not going out, but science knows no bounds, right? So I'd like to give a special thanks to both Sydney and Aaron. They spent a lot of time with us, helped us work through a lot of problems during this project. Without them, half this stuff would have never been done. We'd also like to thank the City of West Kelowna and the Rose Valley Water Treatment Plant for letting us go up to those reservoirs, giving us access and historical data. And then we'd also like to thank Laird Aquatic Consulting, because they provided us with a lot of data as well that we could use to contrast with our results. And that's the end of our presentation. We'll open it up to questions.
Awesome, thank you. So if there are any questions from the audience, throw your hand up, ask your question. I'll rephrase it so everyone online can hear, and then these guys will get a chance to answer. So any questions out there? Yeah, please. So the question is, do we know if the City of West Kelowna has solved the precipitate problem? Yes, no.
I wouldn't necessarily say they've solved the problem, but they are working on strategies to mitigate it.
What are some of those strategies?
So aeration is a big one. So we're talking about nanobubbles up here, which is a little bit more advanced version. But by aerating that water, you're going to change the conditions from an oxidizing conditions or reducing. So when you have that oxidizing conditions, you're not going to get that manganese precipitating out later on. It's going to precipitate out in the lake. So that's what they're trying to do with aeration. Aside from that, anyone else? Anything? No. Cool.
Thank you. Any other questions out there in the audience? Yeah, please. So the question is, would the sampling have produced potentially different results if the reservoir was at a very high level or a very low level?
Yeah, it would. You have stratospheric zones in your lakes, right? So the more depth you have, the more defined these zones will be, and it will affect the contents in each level. How exactly? I don't have enough time to get into it, but depth would change things.
Thank you. Any other questions out there? Yeah, Tom. Great. So the question is about the ultrasonic algae device, and where is this being used? Do we have any evidence of this being used out there? And if not, where can we get some more information about that?
Well, during our research, we definitely came across a lot of examples of it being used and saw how well it worked. That's why we put it in there off the top of our heads. So I don't think do you have an idea?
Yeah, the RDNO put the ultrasonic floats in Goose Lake, and I can't speak to how well it's working because I was only working there for the summer, but they did put them up there.
Very cool. Thank you. Final questions out there before I ask mine? I know.
No questions from the teachers.
Okay, my question for you. So I was working with these guys on this project. My question is, if I gave you 6 months, this is your full-time job for 6 months, and you have an unlimited budget, what do you do now? What would you be most interested in looking at there?
Well, we definitely start in May, so we could work over the process of the summer months.
In the mic, sorry, please, for the, yeah.
We would definitely start this project in May and work over the summer months when the creeks are actually flowing from one another, because when we were doing this one, they weren't open, so we don't actually know if the concentrations were changed as they were flowing from lake to lake or reservoir to reservoir, but other than that.
Yeah, so we looked at the ORP to differentiate which elements would be dissolved into the water and settling out in the sediment. So I think if we had more time and more resources, we'd take samples of the sediment so we could really compare what concentrations are in the sediment and what concentrations are in the water to give us a better idea of what times they would be flowing down into Rose Valley Reservoir.
Any other ideas? That's great. Okay, so all the first years who are thinking about their capstone project in a couple years, you just wrote all that down, right? Because those are all really good ideas? Yeah, awesome. All right, join me again, please, in thanking our first group for their presentation. All right, so as our first group just did a great job of introducing to all of you, the Rose Valley Reservoir has been experiencing some issues alongside some customer complaints. And while the last presentation did focus on the potential impact from the watershed perspective and really looking at those bighorn lakes, this next group is going to look at the other half of the story and do some investigation into the reservoir itself. So please welcome to the stage our next group, the Reservoir Renegades.
Good afternoon, everyone. My name is Gurpreet. Here are my group members, Sadie and Margie. So I'll be talking about the history of the reservoir, why it was important to monitor the water quality of the reservoir. So this is a man-made reservoir built in 1949. It provides water to 7,800 homes in the city of West Kelowna. It was mainly built because of the rising water demands of the water at the time. This reservoir is primarily fed by Lambley Creek through 34-inch steel pipe. The pipe is around 64 meters long and has a maximum flow rate of 0.903 cubic meters per second. So this is the depth profile of our reservoir, of the Rose Valley Reservoir. The water flows from north down to the south. It is deeper around this area here and consistent throughout. The storage capacity is 5.6 million cubic meters, and residence time of the water in the reservoir is up to 2 years. The purpose of our visit was to monitor water quality of the reservoir because of the customer complaints about odor and color. This is what the residents of West Kelowna were experiencing, like the previous group mentioned as well. This is the post-wildfire picture of the reservoir from last year at McDougall Creek. And this can heavily contribute to the elevated levels of metals due to soil erosion and runoff around the reservoir. We went up there on October 23rd. These are our 2 sampling sites. And the samples were taken after mixing of the reservoir in the fall. These sites were specifically chosen because the number 1 is closer to the outfall of the reservoir, so we can monitor what's going into the plant, and site 2 because of the depth, so that we can collect data near sediments. So sample collected, including samples from 2 sites, 2 depths. At each site, we grabbed triplicate samples for precision, and vendor sampler, as previous group mentioned how it works, was used to collect the samples at different depths. So Sadie will take over from here, and she will talk about method analysis carried out in the lab and the results.
All right. So first we analyzed the samples for phosphorus and nitrogen using the hack methods. This includes adding these pillow packs to the sample and reading the sample in that machine there, the DR3900. Unfortunately, our nitrogen results were inconclusive. However, we do have results for phosphorus. So, at the outfall of the reservoir, which is the intake to the treatment plant, we have phosphorus results ranging from 0.2 to 0.11 milligrams per liter. There and there. That averages out at around 0.07 milligrams per liter. This red line indicates the BC drinking water guidelines at 0.01 milligrams per liter. At Site 2, which was in the mid-lake area, we can see that the numbers are much closer in range from 0.7 to 0.9 milligrams per liter. The average here is 0.08. That red line is also the drinking water guideline at 0.01 milligram per liter. Here we can also see that the numbers are much more stable in range versus the intake to the treatment plant, which were more varied. Next, we analyzed iron and manganese using atomic absorption spectroscopy. But to do so, we had to prepare the samples. First, we digested the samples with 2 types of acids, hydrochloric and nitric. Digestion involves heating a sample with acid for a certain period of time, depending on what you're trying to do. This forces all of the manganese and iron into its dissolved form, so we could analyze how much in total there is. Otherwise, there's a mixture of solid and dissolved. After digestion, we used a 0.4 micrometer nylon membrane to filter the sample of any lake water goodies like bacteria or algae to keep them from plugging up the very expensive equipment. Next, we made standards, because somebody's got to have them. But we needed a scale to tell the machine what we're looking for and at what concentration. The AAS works by shining a light at a wavelength that is specific to the element that you are measuring. Your sample is fed into the machine and into the flame where it is then ionized. That wavelength that you had selected shines through the flame apparatus and to the other side where the machine measures how much light was absorbed by those atoms in that flame. All that to say, we did get to play with fire, and yes, it was very cool. Here are our iron results. At the intake site, we can see that the results are about half of that from the results of the mid-lake site. So there's the intake and mid-lake. Our field blanks did test at 0.1 milligrams per liter. We're not sure why, but these numbers could be plus or minus that 0.1 milligram. Here are the results in a graph, illustrating the difference between the 2 locations. This red line represents the BC drinking water guideline at 0.3 milligrams per liter. These are our manganese results, which were 0. We attribute this to the time of year that we took the samples. Here's a graph showing iron over the year from February to November from 2018 to 2024. The blue bars represent older data from 2018 to 2021. The red bars represent newer data from 2022 to 2024. We can see that the new data, the red bars, are definitely showing an increase with time. Notice that the levels are still below the BC drinking water guidelines. for now. Just like the previous graph, but this one is showing manganese from 2018 to 2024, February to November. Again, blue bars represent older data and the red bars represent newer data. This orange line is the scale of the iron chart from before. This green line is the BC Water Guideline for the maximum allowable concentration of manganese. This green line is the aesthetic objective that they're aiming for. So next, we looked at the historical algae and cyanobacteria data for this year, since we were sampling out of season for these numbers. On the left shows the number of algal cells, and on the right is milligram per liter of iron or manganese. Notice the peaks of the graphs in May and August going into September. Here, we compared the iron data to the cyanobacteria data. And finally, we added the manganese data, and we can see the relationship between all three starting to show. When we have these iron and manganese peaks, we are also seeing a huge increase in cyanobacteria. Okay, so what does that all mean? Well, Margie is going to break it down for us.
So what can we conclude from this project? So first, the presence of color in the water can be related to organic or inorganic sources. In this case, our analysis corroborates the city of West Kelowna's initial findings, which identified inorganics, primarily dissolved manganese, as the source of that brownish color that has been present in the treated water. Since manganese precipitates out of solution when it encounters an oxidant, such as chlorine, during the treatment process. Also, the increase in the nutrients input into the reservoir has led to high primary productivity, which is evidenced with the presence of algae and cyanobacteria blooms. So later, all this organic matter that is being produced within the lake undergoes respiration and decomposition, and this is going to drop the dissolved oxygen significantly. This drop is going to change the redox conditions in the water. Finally, monitoring parameters such as pH, temperature, dissolved oxygen, and oxidation reduction potential was fundamental to understand the redox dynamics that were taking place within the lake at different depths. So for example, if we take a look at these graphs, the pH of the water was around 7, and the redox potential was around 0.34. So we can predict for both iron and manganese under these conditions that they are going to be found in the reduced form in the water. This is dissolved. Now, we'd like to share some management strategies. The first one will be a regular monitoring of the oxidation reduction potential, since this will allow the water treatment plant staff to recognize when the redox conditions are changing and take preventive actions. Also, monitoring the algae and cyanobacteria blooms. It is important to identify what is causing the bloom, if it is related to climate change, or if there is any other environmental factor within the watershed that is causing this. Targeted oxygenation near the intake. Research strongly supports oxygenation as an effective strategy for managing dissolved iron and manganese in drinking water reservoirs, since it reduces the migration of these metals from the sediments into the water and facilitates the oxidation, the oxidation of them. The last strategy will be dredging. So when there is a high concentration of these metals in the sediments, a portion of these metals could be removed from the bottom of the lake. But this strategy is very expensive and also involves the risk of resuspending some hazardous materials, such as methyl mercury. So an idea for future capstone projects would be to analyze the concentration of these metals in the sediments and study how these metals migrate from the sediments into the water.
We just wanted to mention special thanks to Aaron, Sydney, David, the Rose Valley Water Treatment Plant, and Larrett Aquatic Consulting for help with our project. So, thank you.
Okay, so maybe I'll give you guys this mic. There you go.
Thanks.
Then do you want to just stand over there, put yourselves in the light? And ask questions. Okay, thanks. All right, so same drill. If there are any questions from the audience, throw your hand up, and I will repeat that for everyone joining us online. Yeah, please, Allison. Okay, so the question is, the nitrogen data was mentioned to be inconclusive. Can you please elaborate that a bit more?
I think that we attribute that mostly to errors in the DR 3900, and that it needs a formal calibration for the college.
Yeah, that's correct.
Blaming our instrument. Okay, that's, yep. Noted. I will pass that on. Any other questions? Yeah, the back, please. So the question is, why are manganese levels in the fall so much lower? And if you'd like to pull up a graph or anything, I could do that for you.
So in the summer, the temperature rises, which causes the cyanobacteria levels to bloom, and they are using up the oxygen in the water, which is then doing some stuff with the redox potential, which is causing that level to rise.
Great. Any other questions? Fun, easy ones are allowed too, you know. Yeah, please. Great. So the question is, how do you know, it was mentioned that the samples were taken after turnover had occurred. What was the indication that that had already happened?
Because the temperature and the dissolved oxygen, the temperature and the dissolved oxygen was uniform in the water column.
Perfect.
Thank you. Any other questions? Yeah, Garrett. What was your favorite part about this project?
The favorite part is this, that it's getting over.
That does not count.
And of course, working with Sydney, Aaron, and everyone, and these guys. That's the best part.
All right, and I'll ask my one final question for you, which is just, what do you think the most limiting factor or challenging aspect was for you guys in your research?
Yeah, we need to plan our sampling, like sampling time and how many samples we should take, so that we don't have to do the last minute adjustments.
Mm-hmm.
That was the big one, according to me.
Yeah.
You want to add?
I agree.
Yeah, developing your sampling plan was the most challenging for sure. Yeah, we worked on that for a long time. Awesome. If there are no final questions out there, last call. Welcome you again, and thanking this group. Thank you so much. All right, and we now have some time built into the schedule to give you guys a 15-minute break before we switch gears. So you've got 15 minutes to use the washroom. There's coffee for sale just outside the door as well. Or if you want to talk to these groups and ask them more questions, they'll be around. So we'll kick back off with our final presentation at 3 p.m. Thank you. All right, everyone, if I can invite you back to your seats and we'll get set up here to do our last presentation of the day. All right, welcome back. Our final presentation of the afternoon is going to change things up a little bit and is looking at investigating practical applications of electrocoagulation, it's a mouthful, as a portable point-of-use water treatment device. So this research is going to aim to address the growing need for sustainable solutions that reduce chemical use and environmental impact in water treatment. The work presented this afternoon serves as a proof of concept study and a demonstration of how electrocoagulation can reduce turbidity and contaminants, offering potential advantages such as less chemical usage and smaller sludge volumes. So please welcome to the stage Aqua Bolt Force.
Hello everyone, thank you for taking time out of your busy schedule to join us today. We are Aqua Bolt Force. My name is Ryan Sather.
I'm Francois Furland.
And I'm Joe Sarek, and I'm going to be starting our Capstone presentation. Portable, energy-efficient electrocoagulation. Coagulation, how does it work? So many people here are part of the water treatment industry or know somebody that's in it. So you might understand some of the terms like coagulation, flocculation, sedimentation, and a clarifier. Coagulation is an important and a vital step in conventional water treatment. It helps bind contaminants in the water for removal. So coagulation is the unstabilization of stable colloids or larger particles in water. In electrocoagulation, it's done by electrical current, and as opposed to conventional means, which is chemically driven. Most particles have a net negative surface charge that includes viruses and bacteria, and electrical coagulation addresses a lot of challenges in water and wastewater with sediments and industrial effluents. So here we can see some stable colloid particles. They won't settle and they're not removed through conventional filtration. And the reason for this is in their natural forms, they have a net negative surface charge, and as they are like charges, they repel each other instead of attract each other. And they're very small particles, so they bypass conventional filtration methods and stay in the water as small particles. So coagulation, coagulation makes these particles unstable. So as you can see here that they're positive and negative. And we do this by partially or completely neutralizing the particles, and that's done through coagulation. So now they're able to come together due to van der Waals forces. So they're attracted to each other and they can agglomerate or coagulate. And these particles now become bigger in size and are settleable or filterable in water. Again, this is a agglomerated particle through coagulation. So commonly we use chemicals in today's water treatment services, injecting such things as aluminum or ferric chloride, as well as other chemical injecting coags. And in our case, in this picture, the aluminum precipitates the aluminum ions onto the surface of the particles, which neutralizes them, and they are now able to agglomerate and filter out. So in electrocoagulation, The aluminum ions are provided by aluminum plates in the electrocoagulation unit. The anode and the cathode are produced by the outermost plates being supplied with direct current. The driver for giving off aluminum ions is the electrical potential difference. Putting these plates in the feed water with electricity helps the aluminum ions participate onto the particle that causes the coagulation. And here are some of the reactions. So in the anode reaction, we have metals dissolving and water oxidizing. And in the cathode, we have oxygen and water reduction. And there's the precipitation of the aluminum onto the contaminant so it can be absorbed. So in electrical coagulation reaction, this is just it broken down. You can use multiple different types of plates. An example here is aluminum and iron. So here's an overview. We have the anode and the cathode with water with contaminants going through. We apply electricity here. And then the electricity helps that aluminum ion go through the water to the cathode. And over time, there's a sacrificial anode, which is the aluminum plate, and it deteriorates over time, causing this chemical reaction of coagulation to happen.
So our goal, our vision, was to make an affordable, portable, rechargeable, and efficient unit for rural and remote water treatment. So what we're going to do today is put on a little small demonstration for everyone. We have built this electrocoagulation unit. On top, we have a 31.5 liter tote. We're just using for source water today for demonstration purposes. In the field, we would pump directly into our primary cell, which is our reaction cell. We have some aluminum plates in here that we've cut to size. What you see Francois turning on is our battery, a portable battery pack. It is rechargeable through solar panel or via a vehicle. It's a 12 volt, 10 amp output, which we run AC into this unit, which converts it into DC. We can control our output. We have it set fairly low right now. We're going to turn it up so you guys can see a small reactions happening. Francois is just introducing our source water into our front cell to help move it along. Can we get the lights, please? I'm turning it up right now. We're going to get her coagulating away. And as you can see, this cell is becoming quite murky, starting to spill over into our second cell here, going underneath one of our baffles, and it'll make its way over a series of weirs and under baffles till it gets to the end. This unit can do a rate of 3 liters per second, running it through a 1 micron filter at the bottom to a collection tank that we also have at the bottom here, which is the same as our top, a 31.5 liter. Can everyone see that out there? And you see now it's moved over into our third cell. Now we're going to keep this running throughout the whole demonstration here. So you can see by the end, you'll see a lot of particulates. Now what's going to happen is you're going to get a lot of hydrogen gas floating a lot of our particulates to the top. They will settle over time as the hydrogen gas dissipates. Lights, please.
So how we got here. So our design idea was to make a EC unit, electrocoagulation unit, to be able to supply water for 4 adults per day. As Ryan mentioned, we're able to supply 3 liters of water per minute with a battery capacity that can last between 5 and 8 hours, depending on the water source itself. We wanted it to be rechargeable through solar power or through perhaps a car battery, so that it could be used for emergencies or in rural areas. Why did we choose to use electrocoagulation? Electrocoagulation is versatile, scalable, energy efficient, has high removal rates of particles, it's adaptable and flexible in nature, has no chemical costs, can kill viruses, cysts, and coliform bacteria. It can eliminate exposure to harmful chemicals, and there's no hazardous waste disposal. Another key benefit of electrocoagulation is the reduction in solid weight. So because of the oxide particle that is produced instead of a hydroxide particle, less water is retained in the particles. This results in a lower weight in solids and also allows for faster filtration rates. 100 grams of aluminum plate can produce 40 cubic meters of treated water. With the help of filtration, electrocoagulation can remove pharmaceuticals, microplastics, fog, so fog is fats, oils, and greases, BOD, TSS, TKN, bacteria, viruses, silica, metal, phosphorus, cyanotoxins, hydrocarbons, colloidal clay, and polymers from water. Electrocoagulation also has a high removal rate of various particles. With our project, there's a few things that we haven't had time to test out fully. We haven't had time to test the electrodes to capacity, so maintenance and replacement hasn't been tested yet. We haven't been able to test the amount of sludge it produces and how to dispose of it, optimizing power, ensuring functionality and proper operation in the field, and what it can remove at what rates. We're hoping that future students in the WET program are able to take these and bring them forward in the future. With the help of our teacher, David, we've been able to develop a lab for help so that they can use this lab in the future to provide some of these answers. We're hoping that they can make advancements in the materials and designs, experiment with different rates, current optimizing, and more testing and trials. In conclusion, electrocoagulation is a promising, sustainable water treatment technology with key benefits that include cost effectiveness, versatility, and environmental friendliness. We're hoping with continued innovations, this application can be brought into different fields of water treatment. We'd like to thank our teachers, David, Owen, Sydney, Allison, Frank, and Aaron. Thank you.
Right here, bud.
Questions?
Yeah, we'll take questions from the audience now. Please, Riley.
Yes, Riley.
So the question is, could this be hooked up to a well and be drunk immediately, or is secondary treatment necessary?
I guess it all really depends on the water source, what's the well. Usually you do need filtration, like I said. If there's a way to get the water out of the bottom of the tank without filtration, and there's none of the cement on there, then you help it, but depending on what's the well.
Turn it off. Sorry. That's okay. Don't.
Do you want to summarize that again in one sentence or less?
Okay. Depending on what's in the water, essentially, but it's practical. It could happen without secondary treatment.
Other questions? Yeah, please. So the question is, how fast does it treat the water?
Yeah, it almost does it immediately. We usually just let it run off for about 10 minutes prior to setting it up to our filter, just to make sure that we are having coagulated water with sediments going through a filter.
Hard to see in the dark, but there's a couple at the back, yeah.
Can this be expanded to be like a big water treatment plant for like 1,000 people or so?
Yeah, so the question is this scalable to large-scale water treatment?
Yes, it is scalable for large water treatment. It is being used for wastewater treatment as well as industrial water treatment. So it can be used for water treatment as well at a large scale. And it is being used, just not usually in municipal water treatment.
Other question at the back. Great question. Okay, so the question is, compared to a chemical-based coagulant, how much less aluminum does this method use?
I don't really have an exact answer to that, but it's a lot less. There's no chemical transporting costs or any chemical safety involved in this. It's just cheap aluminum plates that you can get from anywhere. You can get it from a scrapyard and get them retrofitted into a coagulation unit.
Another question at the back. Question is, what are large-scale uses that are happening right now with this method?
Yeah, mostly military uses, wastewater treatment, and industrial treatments like mining and oil and gas.
Garrett. So the question is, what would be the footprint for a municipality compared to current methods being used now?
I guess it would be a lot smaller, but it'd still probably be around the same, just because you do need a coagulation basin with the plates inside, and time for filtration and settlement.
Yeah, I was about to mention that filtration would still need to occur, so you'd still need the capacity to filtrate. So it wouldn't change that much based on the amount of filtering you need.
But it would be smaller because you wouldn't need the mixing time. So it would probably be a basin or two smaller.
Another question at the back, yep. So the question is, could you use DAF, dissolved air flotation, as opposed to filtering?
Yeah, yes, you could. You could use DAF to get the solids to the top, and then you could rake them out, and then over time, through your baffles and stuff, you have clean water at the end.
All right, so my question for you is, what is, as you see, the biggest pro or biggest difference for your unit compared to the things that are being used out there right now?
Yeah, we kind of did mention that, and it's chemical costs for sure. If anybody in a rural area or need it for emergency, you're probably not going to get chemical transported emergency, and this can be readily available anywhere.
Can I just ask, do you mean ours compared to other EC units that are available?
Yeah, that was my
Okay.
intention, yeah.
So an example, we also use EC units in the program. Some of them can cost upwards of $7,000 for just a small little unit about this size. We were able to make ours for $400 or so, and at a much larger scale as well.
Thank you. Any follow-up questions? Yeah, Aaron. So
Yeah.
let me just repeat the question, sorry. So Aaron's question is, was any testing of the water quality done before and after?
Yes, Aaron, there was, but up until about 2 weeks ago, we spent a lot of time designing, researching, building the unit that we were tasked with building a lab and building a user manual. So we did do tap water through it. The results were better, but we never really got a baseline for a lot of the things that it can remove, like we noted in our presentation.
Okay, and I'll open up one more question. We have time for one more question if there's something burning out there. All right, fantastic. Well, everybody, thank you. Yeah, we can leave this up here, and at the end of our presentation today, feel free to come up, take a look, interact. Could you keep it on the side there, though, guys? Yeah, cheers. Because at this stage, what I'd love to do is invite up all of our professors, so your lecture professors, your lab professors, whoever's in the room right now, please come up and join us on the stage, because we are about to award our presentation for Top Student of the Year, and we'd like all of your professors here to hand over that award. If you want to just, yeah. That's it. Anyone else hide? Allison's going to take some photos while you guys hand it out. If you want to stand in the light, please. She's going to take photos, but if you can just stand in the light. All right, so each year we award this award to a student who exemplifies excellence in the water engineering program. We ask our faculty and our students to nominate and vote for the student who they think is a community builder, a technical specialist, and a leader in their program who shows up every day with a positive attitude and a desire to learn. And this year it is my absolute pleasure to present this award to Rosina. So if Rosie could please join us on the stage. Come on up, Rosie. You guys can just move up to the light so that Allison can take photos. Frank, up to the light, up to the light. Here, let us open the award and show off the award. It's very pretty. Yeah, don't drop it. It looks also very breakable. There we are. Thank you so much. Yeah, congrats, Rosie. There you go. Cheers. So we're not done with her yet. Because we did put out that vote, I was able to summarize all the comments that happened from both the cohort and the professors and why Rosina won this award. So what I would like to say is across all those comments, there were some really common themes. Rosina is highly regarded for her strong academic performance. I can attest to that. But more importantly, I think, her work ethic and her positive attitude. She is dedicated, she's hardworking, and consistently helps her classmates, fostering a cooperative and supportive environment. She's approachable, modest, about her intelligence, and she's always willing to help others. She's also praised for her commitment to learning and contributing to the community, particularly in the context of conservation. And you can always count on Rosina to show up. I don't just mean attendance, although she usually does, which is fantastic. I mean in a bigger context. She shows up and constantly demonstrates her abilities as a leader and her responsibility. So one last time, thank you. Student of the Award of the Year, Rosie. Congrats. Yeah. You can just stay here for a second. And now we'd like to invite everyone who presented, all of our graduating students, up onto the stage for a final farewell and photos.
Closing remarks?
Yeah. All right. That order up.
We'll get closing remarks. All right. Wait, one picture, then do closing. Okay, we just have a closing remarks. For the first time in my career, like I was telling my colleagues, I actually wrote something down just for this group. So it's actually a little harder than actually just coming up and talking, but nevertheless, I wanted to capture the moment correctly. All right, first off, I'd just like to thank the students, the colleagues, the friends, and your family for being here today. Water engineering students, class of 2024. I remember 2.5 years ago, your first day at Okanagan College. Lots of new faces, lots of uncertainty in your eyes, and what to expect in the road ahead. I think you'll all agree, looking back on your experience, that road to success is always under construction. And a path with no obstacles, in sense, doesn't lead anywhere. So here we are today at the completion of today's capstone presentations. These projects illustrate the confidence you've gained over the last few years through making a commitment to education, collaborative learning, and meeting some new friends along the way that helped out in times of need. You've all worked so hard in class, and you've all accomplished so much, but it's just the beginning of good things ahead. Never be afraid to continue to work hard, try something new, explore all your interests and passions,
You truly have the power to achieve anything you desire. Enjoy the journey that lies ahead of you. As a professor, and I speak for all of us, it's been a privilege to teach you, guide you, and maybe in some small way even be a mentor. So I can't, thinking back over the last couple of years, I don't know how much caffeine I've consumed with this group, but I do want to have one final cheers to the group. The final rock star on behalf of this group. And I want to post cheers to the end of this chapter. To all the challenges you've overcome and the lessons you've learned along the way, what may feel like the end being here today is kind of just often just the beginning of something new. All right? And secondly, cheers to the past memories and the new ones that await ahead in life. Onwards and upwards. Thank you. Thank you all.
Thank you.
And thank you all for coming again. Appreciate it. Hope to see you here next year.
All right. It's done, eh?